I'm starting with second law. So you see here, second law can be stated in many ways. Okay. So right here can be stated in many ways, but the main concern of second law is this. Here second law is that is net net heat flow net heat flow uh, net heat flow um, is is from high temperature to to lower temperature without doing any external work. Okay, means we cannot heat cannot flow from high temperature heat cannot flow from the temperature low temperature to high temperature without doing external work. Okay, so means in general heat flows from high temperature to low temperature. So it can be stated in many ways. The first statement or one statement is this Kelvin statement. It is impossible to convert heat from a single source into work without any effect. That means what? It's here we cannot produce this kind of engine, in kind of perfect heat engine that converts total heat into work. So this is impossible. Okay, this kind of engine is impossible. Similarly, we cannot have that kind of perfect refrigerator that converts heat from low temperature to the to the high temperature without doing extra work. Okay, so this means the 100% perfect engine is not possible. So this basically talking about this thing. Okay, the another statement can be said in that way is called the Clausius statement. It says that heat never flows spontaneously from cold temperature to high temperature. Okay, so these statements are same. They are not different statement, but we are the meaning of this both statement is same. So um, in in summary, we can say like this is 100% efficient uh, engine or refrigerator, okay, is not possible. You cannot produce this kind of machine. Okay, so even even in even in even in perfect the ideal situation, we come across this situation. This called the Carnot cycle, Carnot engine. Even we consider the perfect ideal situation, we'll see soon that 100% conversion of heat into work is not possible. Okay, this will not possible. We come across this point very soon. Okay, so this means what we are saying is that still principle of conservation of energy exists. It's always true. So what we are saying is that what we have the total useful heat energy, that gets converted into some this energy, some is converted into work and some is converted into the unuseful unuseful energy. So what in unuseful energy means this energy cannot be converted into work. Okay, so we have two statement. Just we saw one is the Kelvin statement. Yeah, Kelvin statement, or we also call it Planck Kelvin Planck statement of second law is this. This basically defines the heat engine. Okay, so this basically defining the heat engine. And second is we just saw is that Clausius is the Clausius statement that basically talk about the refrigerator. Okay, that talks about refrigerators. So okay, so but these both statements are equivalent. So both statements are equivalent. They are talking about the same thing. Okay, but there are only different way to state that. Okay, so next we'll talking about the ideal situation of the Carnot engine. So in this picture we combined a perfect refrigerator, means heat flows from low temperature, this temperature is low temperature to high temperature. Okay, and we are combining other engine is the heat engine. So if we combine perfect the heat engine and perfect the refrigerator, then according to our second law, this is not possible. So this kind of engine is not possible because it will actually going to transfer heat from the low temperature to high temperature without doing any external work, without doing work um, on the system. So if the Clausius statement is false, then Kelvin's statement must also be false. Okay, so this telling you that both statements are same, or in terms of meaning, they are equivalent. Okay, so in this engine, in this picture, two coupled engines, D and E, one engine is D, other engine is E, are working between the same temperature. So the high temperature and the temperature, this low temperature, both the engine is same. And if they are so according to this picture, we can say that the all reversible engine operating between the same two temperatures have the same efficiency. Okay, so now let's start with the ideal engine, ideal cycle. So this Carnot engine is the ideal engine. Okay, ideal engine. So it will give, this engine will give the maximum possible theoretical um, efficiency of heat engine. Okay, that will gives the is four means that will gives the maximum theoretical efficiency. So ideal engine means we are ignoring all the frictions. So we ignore friction, means there is no friction between this this cylinder and piston. So this is the, we have cylinder here. Okay, so this is a piston here. We are assuming there is no friction, and we are also ignoring the heat loss. Okay, so we are also ignoring ignore heat loss in any other forms. Okay, so let's start to this cycle, Carnot cycle. It goes through 4 cycles. So we'll step we're going to discuss all these steps. Step 1 is isothermal. Step 2 is the adiabatic. third is again isothermal, fourth is again this this is called the adiabatic. Okay, so let's talk one by one. So in first step, isothermal expansion means, so for simplest example, we can say this is cylinder with a piston. We are supplying heat to the system. Say the furnace has temperature TH. So we want this, if we supply the heat, the piston will go up. So this is the isothermal process. Okay, so this is the isothermal. We are supplying the heat, but temperature remains this temperature remains constant. Okay, this temperature remains constant. In second step, we call it the adiabatic expansion. So what does it mean? In this case, volume will increase. This expansion could happen, but we are not supplying external heat. So we put in the insulated stand. So insulation, so it will not lose the heat. So in this case, dq heat is dq, we supply heat, so dq is 0, dq is greater than 0. Here we are not supplying any external heat, so dq will be 0. Okay, so this is the adiabatic expansion. Again, the system, again the cylinder, the cylinder is going to, we have to use the cylinder with the piston. In this time, this cylinder is this system, the system of gas is here. It is actually going to lose the heat to the temperature at the atmosphere. So its temperature is called Tc. So in this time, it will go to lose the heat. So dq is less than 0. So this is isothermal. This is the compression. And final stage is that again, this is the adiabatic compression. Adiabatic compression means, again, it will not going to lose the, we are not supplying any heat to the system. Okay, so this means in this case, the heat supplied to the system is equal to 0. Okay, so we went through for this process. So this can be represented in this this curve, this PV diagram for this engine, for this ideal Carnot engine. So as a representation, this will represent the engine. So this engine, heat engine, is working between high temperature TH and the low temperature TC. So this is the temperature of source. This is the source temperature. Okay, so this is the source, and this is the temperature for the sink. Okay, so we're talking about these things here. Okay, so now this engine here is, for example, simplest case, this engine in our case is the cylinder with piston. Okay, so now let's start. We are doing some math to find what is the efficiency of this heat engine. Okay, so it started with the point M. Okay, so it started at point M, then it goes through the cycle isothermal expansion N. So it will be after this end, it will be at the point N. So heat flow from, so this will show that path is along M to N. Okay, so this corresponds to this first picture you see here. This is isothermal expansion. Let's do it. For that, so in this picture, you see, I just say that M corresponds to coordinate system state PM, pressure at point M, volume at point M, and temperature is at that time is TH. Okay, and it is N is the final position, and the final state or position is Pn, and it will be Pn. It will be say T TH. Okay, so I'm representing only these sections. Okay, only for this section. So this Mn will basically represents the thermal expansion. Okay, isothermal expansion, and here QH, we write QH is the heat supplied, and in this case, change in internal energy will be going to be 0 because there is no change in temperature. So, but we have work. dW is greater than 0 for these sections, for M and N. So we are talking about these sections. Okay. If you see here for the point O, O point has a state PO, pressure PO, volume V naught. V naught means corresponding to point O, and temperature Tc. Okay, so if this is the point for the path for this state for NO. Okay, if we take this path NO, this is the adiabatic expansion. So this NO is the adiabatic expansion. In adiabatic expansion, if for this part we can write that our change in internal energy is not equal to 0. Okay, but our heat supplied dq will be 0, and we have work is greater than 0. Okay, so these 4 part curve NO. If now we move to the point OP. Okay, so let's go to the P. If you see the point P corresponds to pressure P, say PP, volume VP, and temperature is Tc. So here OP, say for example, OP is the isothermal compression. Okay, isothermal compression. We see that QC. So we can write here. We see it will going to reject the heat. So QC is the heat rejected to the sink. So in this case, sink is the environment, the outside the cylinder. So in this scenario, work will be less than 0. So we can say dW work is less than 0. In this case, temperature is not changing, so your internal energy will be 0. Okay, so this is for this curve OP. Okay, this is for the OP. So let's go to the final stage Q2M. Okay, so let's go to Q2M. Okay, so we are now here again. We are here from P to M. Okay, so for point M again we come to the initial state. So finally we come back at initial state M. So you know M is already PM, pressure is PM, volume is VM, and temperature is TS, right? It's high. It started with a high temperature. Okay, so if this is the case, you know that PM is the adiabatic compression. Okay, for adiabatic compression, you see we are not supplying any heat, so dq will be 0. Your work done in this case, this is the compression, so your work done will be less than 0, and there will be change in internal energy, so this should not be equal to 0. So this is be true for that. So this is the explanation about the curve. So you know that this area under this curve, this represents but the area, so area under the curve MNOP, okay, so this is MNOP, this area, okay, so I'm writing here again back, is curve is start is this area MNOP, this area will give total or the net work done during all four processes. Okay. So our next goal is to find, our goal to do the math, to find, our goal is to find efficiency of Carnot engine. Okay, next my goal is this, how I can find the efficiency of the Carnot engine. Okay, so let's start with for the curve, this part isothermal expansion MN. So for the MN we can use the first law. So first law is to every time, so delta Q will be equals to delta U plus delta work dW. Okay, so in isothermal we have it go from state M to the state N. Okay, so temperature is constant, so dW du will be 0. So we can write this, in this time we supply the heat QH, this will be equal to work done from M to N. Okay, so we know from previous topics that this work done in isothermal case will be NR T H over times log Vn over Pm. Okay, so we figure out that part. Again, in for this for the curve NO, it will go from state this one to the state at O. Okay, so for that part again we can write the same equation, delta Q equals delta U plus dW. In this case, this is the adiabatic expansion, so this will be 0. So we can write minus, if we take the other side, delta change in internal energy from N to O equal to this total work done. This will be WNO. Okay. And next, you go to the for PO. In the PO, it will go from state P. This is the state P. Go to the state. It go to the state O from the state P in this portion. Again, as before, so we can write QC. This will be the, this time it will be rejecting the heat. QC change in internal energy will be 0. So work done will be from O to P. Okay. If we do the, if we include the what is the work done during this, so this will be equal to nRT. Temperature constant is Tc. O times log Vp over Po, right? For the state Pm, it will go from in state P, go to the initial state, and M, we can write as, in this case, according to the first law, change in internal energy, energy from P to M, it must be equal to work done from P to M. Okay, so you know that change in internal energy basically depends on the temperature difference. So temperature difference for this section, temperature difference for NO section, and temperature difference for the PM section will be same. So internal energy is same. This means work done will also be the equal and opposite for Mn and and this part MO, so they will going to cancel each other. Okay, now we are using the concept of efficiency, so we can write as you know, as before we can write E Carnot equals total work done over QH, it's applied. So this will be QH minus QC over QH. So this will be equals to 1 minus QC over QH. This is the efficiency of Carnot engine. So we haven't done anything new here. We have used this equation, similar equation before. So our main concern is how to find. So to find this QC over QH at first. Our whole goal is this. Okay. So we have this result QC and QH. From here, QC is this value and QH is this value. So we can plug in those number over here. So okay, so we got it. So let's try this only for now. So QC over QH equals NRTC log VP over V naught. QH will be replaced by NR TH log Vn over Vm. Okay, Vm over Vm. So these will cancel out. So we are left with QC over QH equals TC over TH. Okay, TC over TH, and TC over TH. Then we can do log Vp over V naught, okay, over log Vn over Vm. Okay, so our goal is to find how to simplify this part. Okay, now we can use the equation we have to solve this part. Okay, so let's start with you can start with for NO, which is adiabatic curve. Okay, so for this curve we can write TP gamma minus 1 equals constant. Okay, so this gives you that we can write for that T H Pn gamma minus 1 must be equal to, for the OTC, P naught gamma minus 1. Similarly, we can write for Pm is also adiabatic curve. Again, I'm using the same equation. The same equation will give you TH, okay, TH Pm gamma minus 1 equals TC for the point P, Vp gamma minus 1. Okay, so I will use this and this, and I'm going to write this as THPN gamma minus 1 over THPM gamma minus 1 equals Tc V naught gamma minus 1 over Tc Vp gamma minus 1. So that will give you this this cancel out. So this gives you the relation between the volumes, because Vn over Vm gamma minus 1 must be equals to V naught over Vp. It will be power gamma minus 1. So we can write this as Vn over Vm equals V naught over Vp, right? So we have this result. So I can combine this result and put back over here in this part. I'm going to replace here. Okay. If I do that, then I will find QC over QH equals minus TC over TH log Vn over Vm over log Vn over Pm. So this will cancel out. So we are left with QC over QH is equals to minus TC over TH. Okay. So if we just take the magnitude, we can write QC over QH equals to TC over TH. Okay. So this will be true for the Carnot cycle. So true for Carnot cycle. Okay. So once I'm going to plug that value at the very initial, you see that our initial starting point is this. So if this is the case, I can do it like this. So E Carnot, so I can write E Carnot efficiency for the Carnot engine is, I can write like this, is equals to 1 minus QC over QC over QH. This can be replaced as E Carnot, which is equals to 1 minus TC over TH. Okay, so this are the key equations we'll be using throughout the this topic. Okay, this equation and that is all are the equivalent format. Okay, so this tells you that for E Carnot, efficiency for Carnot engine will be 1, or we can say as 100% if you write in percent. Only possible if temperature of sink should be 0 Kelvin, which is impossible to attain. Only in that situation. Otherwise, we'll have certain value of the Carnot efficiency. Means we are not getting the 100%. That's how it supports the second law. Okay. So we'll talk about the Carnot refrigerations. In this case, just reverse thing will happen. Means in this case we need heat flow. We're talking about the total heat flow, net heat flow from low temperature TC to high temperature TH. But in this case we need work done on the system. Be careful that. Not work done by the system, work done on the system. Okay. So this point important, because now we have to supply the heat. Well, in this case, we have to do the work. So we have to do the external. So need to do external work on the system. Okay. So in this case, just reverse of the Carnot heat engine will be possible here. So in this case, as before, we define k value, value, uh, k value equals, we defined as before, QC over work done. This equals QC, okay, QC over work done, which is QH minus QC, okay. So you define that way. So you know that K is called the coefficient of performance, okay. If we repeat the same step, similar repeating similar steps as for Carnot engine, okay, Carnot not engine, we can show that this K value is K for the, we say, Carnot. This is true for all engines, okay. So this for the K Carnot, if we repeat the same process, we'll get that it will be equal to TC over T high temperature, TH minus TC, okay. So TC is the temperature of sink, okay, and TH is the temperature of source. So we can use this equation to solve the problems for the Carnot cycle. Okay, so every time if we are talking about the Carnot engine or in the form of any kind of engine, we can say that no engine can be more efficient than a Carnot engine operating between the same two temperature. So Carnot engine is the ideal scenario that gives you the maximum possible efficiency between two temperatures, TS and TC. Okay, so if you then you can practice this question. So this question is based on Carnot engine. Okay, so you can try that.